Okay, next steps. Now we are in a quasi-orbit. Now we are at the comet. So of course our next task from the lander point of view is to select a good landing site, to find a good landing site. First of all, everybody of us was of course surprised when we saw the comet is not a potato, it's two potatoes, or a duck, or as you want. So we did some preliminary analysis on both the illumination of the comet and also potential landing sites we could reach with the flight dynamics, with the aspects I was showing before, and with a reasonably means not too long descent time from orbit. And what you see here is a very, very preliminary analysis performed at CNES on possible areas. So you see around the head and the shoulder of, if we stay with the analogon of the duck, we think we could land. Of course, this is really dependent then on the density and also the surface roughness, which is not considered in here as well. And what you see here is, again, a model, 3D model of the nucleus, and everything which is red is more or less permanently illuminated. It's like the summer pole on Earth, and what's bluish is never illuminated, and what's orange and yellow is somewhere in between, and that's what we want. We want to have a clear day-night cycle also for scientific reasons. Yeah, okay. So here you see again our friend, the comet, but now with a clear definition of the pole and the longitude-latitude grid. And this is now a combination of the illumination map with possible landing areas under certain constraints. One can play around with this by modifying the descent time or the density. Well, we cannot play around, but the comet will show us what's the density eventually for this. Okay.
I think we're good. Yep.
Okay,
so,
thank you.
Thank you very much, Stefan. Questions from the audience on this incredibly complicated roller coaster ride, which we will all be back for, hopefully. So if we bring the microphone, somebody standing in the middle, in the front here, in the third row. Hello, microphone people? Oh, sorry, very good.
Thank you. David Schuckman again. On the question of the type of surface, I think you mentioned that there's an understanding now that it's softer than you thought, but I sort of missed that. Perhaps you can explain why you think it's softer and how soft and so forth.
We do not know the surface strength. There is some indication, if you look at these pictures, that it may be more dusty than really icy. When we designed the lander, we had an understanding that comets may be like solid ice, still porous, but solid sintered ice with dust grains. We've simulated this kind of material in various tests, and this would be very, very hard. If the surface is more like regolith covered, under these low gravity conditions, it may be very soft. Some people use the analogon of cigarette ash. You may use the analogon of new fallen snow. So very, very soft. But actually we do not know it yet. And it's not clear whether the images and the data from orbit will really help us to understand the surface strength. So we will only find out when we land there and when we touch down.
Down here in the front.
Thank you. Leo Enright with Irish Television. I was just a couple of questions, if I may. Can I clarify where the rotational axis is? It goes through the neck of the duck, does it? It's
well, if I go back here...
you can hold on to the real object.
I can hold on. It's something like here it goes through. So it's it's very bizarre rotation.
Through the neck?
Yeah, well, if I go back in the presentation, I don't know whether...
Yes, I did see it.
You saw it. You saw the pole.
So you consider that accurate?
This is pretty accurate, what we learned so far. It's not wobbling. This was one of our fears in the early phases. So we are lucky in this respect. It seems to be a stable rotation around these axes I've shown you on the image with the grid and the pole. Yeah.
And my other question was to do with the landing sequence. After release, but before you hit the surface, can that cold gas system allow you to maneuver? Will you be able to pick a landing site in real time?
No, we cannot do that. There is no autonomy to steer around. Obviously, due to the long lead times, we cannot play with the joystick either. The cold gas was foreseen in the old days when our target comet still was Wirtanen, the smaller comet. It was considered a possibility to use it to have a more rapid descent and to use it. Now Churyumov is bigger, much bigger than Wirtanen, so we do not need it anymore. We will touch down, as I said, with a touchdown velocity in the 1 meter per second range. So we now only plan to use this system immediately after touchdown to avoid rebouncing.
But let me ask a follow-up question just for the audience here. Typically, if once you deploy and all the simulations work out, you can't pinpoint land, but you have what's called a landing ellipse. And roughly how big is that on the scale of the comet, which is behind you now?
Landing ellipse is fairly big. It's about 1 square kilometer. So we can choose an area about like this, you know? So we cannot really pinpoint down. And this is to a large extent due to the uncertainty of the orbiter position because of the gas drag in the coma. It's again a bit depending on the actual site we choose and on the mass and the density, but it's roughly in the order of a square kilometer or a bit less, 3 sigma. So it's a fairly big area we have to find.
Okay, in the interest of time, I'm sorry, if we have time at the end, we'll come back to more questions, but now we have to break in the sequence at this point. I'd like to welcome up, thank you very much, Stefan. First, Larry O'Rourke from the Science Ground segment down at ESAC, our